Hello everyone. I'm Lalit, and I'll be discussing on week one. A few questions related to week one lectures. So I just wanted to confirm that everyone is here for the computer vision course, right? If there is anyone who is not intended to come here, they can leave. That's fine. So yeah, we'll actually solve a few questions out here, and if you have any doubts, you can just unmute yourself and speak out. It's fine. Is my screen visible? Um, if it's not visible, you people can raise it. I think it's visible. Okay, so okay, yeah. So we'll start with the first question for today's session. We are given a grayscale image with all its pixel intensities lying between minimum value of 130 and maximum value of 190, and then we need to linear we need to stretch the function in a linear fashion such that the max min is stretched to um, the max min is stretched between 0 and 255. So this is the kind an instance of contrast enhancement, kind of pre-processing that you would have seen before binarization in the lecture. So okay, we'll try to solve this. People are able to see my pointer, right? Yeah, okay, right. Yeah, I hope my voice is clear enough. Or maybe if it's not clear, you can just raise it out. Okay. So I'll try to do it similar to a blackboard session rather than just showing the slides, so that it's more interactive than seeing NPTEL videos. Okay, so we are given minimum value as 130, maximum value as 190, and we just need to use the function given out here. Function is x minus minimum, which is 130, upon max minus min. Yeah. So just for the people who joined just now, we are trying to we are trying to enhance the contrast of the grayscale image by using a min max linear stretch function, and we are trying to stretch the function between 0 to 255 from the current given values 130 to 190. So if we just try to simplify it to some extent, it's x minus 130 upon 16 to 255. So what's the question? So we need to compute the original pixel value x given the corresponding stretched value fx is 85. So you're given that fx is 85. Fx is equals to 85. So we need to find the corresponding value of x. So we'll just replace it in equation 1. So 85 equals minus 130 upon 60 to 55. And if we try to solve this, we get the value of 150. So I hope this question is clear. If you have doubts, you can just raise it. Okay, so we'll move on to the next question. Okay, so we are given two images, I1 and I2, each of dimension 64 cross 64. Both the images have equal number of pixels corresponding to background and foreground. If a pixel is selected at random from one of the two images, it is found to be a foreground pixel. So what is the probability that it is drawn from the image I2? Okay. Okay, few people are still joining. Okay, so what are we given in this question? So we have probability of foreground given image I1 is half. Why is that case? Why is that the case? It's because we have equal number of pixels corresponding to background and foreground. So again, since we have equal number of pixels, so we have probability of background given image I1 is also half. Probability of foreground given image I2 is half. Since both the images have the same probabilities, probability of background given image I2 is also half. And it's also given that if a pixel is selected at random from one of the two images, so that means probability of choosing the image I1 and probability of choosing the image I2 is the same, which is half. So what is the probability of the foreground pixel? So from probability theory, there are a few properties that you would like to use here. So probability of foreground is what? Probability of foreground intersection of with these two images, because these two images are the whole sample space out here. Given this, we can write it this way: probability of foreground intersection image 1 union foreground intersection image 2, which is, since I1 and I2 are different images, so these events are disjoint. So I should write it, I guess, for more clarity, that events are disjoint. Okay, so once these events are disjoint, it's just the sum of the two probabilities. once we have this from base theorem, we know that. Okay, I should write that probably. Maybe I'll just take a shape. Pro- Probability of A given B is, we don't even need the base theorem out here, so it's the simple definition of A. Probability of A given B is given as probability of A intersection B given by probability of B. So we'll use this to get what? So it will be probability of foreground given I1 into probability of I1 plus probability of foreground given I2 into probability of I2. Okay. So these all values that we checked earlier are equals to half. So which gives us probability of foreground is half. Okay, is this question clear?
Hello.
Yes.
So they have asked for finding the probability of foreground pixel given it is like it is from selected as I2, right? So where we are calculating only from probability of foreground.
Okay. Yeah. Okay.
So we need to calculate probability of I2 given X, right?
Yeah. Yes. Okay. So I think these calculations were not required then, I guess. Okay. So we need, okay, probability of I2 given F. Okay. So how this can be written? Probability of I2 intersection foreground given probability of foreground. Okay. So how this can be written? Probability of F given I2 into probability of I2 upon probability of foreground. Okay, so we need the calculation that we did before. That's fine. So what is probability of foreground given I2? It's half. What is the probability of choosing the image I2? It's also half. And what's the probability of foreground is also half. So it's like half into half by half, which gives us half. So the probability of choosing the pixel I2 given that it's a foreground pixel is also half. Okay. Okay, yeah, I guess that is, yeah.
So like how do we like can we like normally calculate probability of F like using the like number of pixels there?
Oh, okay. So they are given a 64 cross 64 image. So that means the
Yes.
number of pixels is, so 64 is 2 to the power 6, right? So it's 2 to the power 12 pixels per
Yeah.
image. So it's like have equal number of
4096.
pixels corresponding to background and foreground. That means 2 to the power 11 pixels are corresponding to background and 2 to the power 11 pixels are corresponding to foreground. So for each of these you can write it in this way. This is obtained by 2 to the power 11 image, I mean 2 to the power 11 pixels of foreground given by total number of pixels in image 1. Okay. So again the same thing applies here. 2 to the power 11 pixels for image, for the background in image 1 upon 2 to the power 12 pixels for the total number of pixels in image 1. Same principle applies for the image to.
No, like I was asking, like there will be total, like so in image one there will be total number of pixels is 64 into 64, which is 4096, right?
Yeah,
So in if it is 4096, so background pixels will be half of the 4096,
yeah.
and
Which is
like
this?
foreground will.
Which is this? This is 2048. This is 4096.
Okay, okay, got it.
Okay.
Yes.
Okay. Yeah. Anyone else has any question on this? Okay. So there is one more question similar to what we did here, but related to probability theory. Okay. So we are given a standardized normal variable set, which means if we write it mathematically, z is a normal random variable, which is standard in the sense that it has zero mean and unit variance. Okay. And it's also given to us that probability of z taking a value less than 1.25 is 0.89435. Okay. So then we are given a, okay, the heights of a group of adults, which is again normally distributed, but we are given the mean and the deviation. So let us call that random variable x. X is the random variable corresponding to the height. Okay. So it's also given that x is normally distributed with some mean mu and variance sigma square, where mu is given as 160 centimeters and sigma is given as 8 centimeters. Okay. So if we now select an adult randomly, randomly means in this case with the distribution given here, mu and sigma square of the Gaussian random variable. What is the probability that his or her height is greater than 170 centimeter? So what our ultimate aim is to find probability x greater than 170 centimeters. So we can just try to manipulate it in this way. Probability x greater than 170 is okay. I'll just try to take this as less than equals to, so that the notations are consistent. So if we can write this as 1 minus probability of x less than 170, less than equals to 170. So since we know that these two sets are disjoint, x greater than 70 and x less than equals to 170 are disjoint, so those two will sum up to 1 since they cover the whole space. Okay. So now I'll just try to linearly shift it. So since we have mu 160, I would like to shift it by mu and try to divide it by sigma. So I'll also do the same thing here, but now with these specific values. Okay. So if we have this probability of x minus mu upon sigma is less than equals to, this turns out to be 1.25, which was given in our question. So what is the distribution of this specific uh, variable that you see, x minus mu upon sigma? I'll For now I'll denote it as h. What is the distribution of h? Can anyone say that?
A normal distribution.
Yeah, it's a normal distribution because x is a normal random variable, and we are correcting it with mu and sigma, so it gives us the standard normal, which is nothing but what we saw earlier. H is also coming from 0 and 1. So okay, we can just put this inside. So with this, I can just replace it by h less than equals to 1.25, and we are given this value of 0.89435, which leads us to the following answer: 0.10565. Okay, is this question clear? So we ultimately found the probability that x is greater than 170 centimeters. X is the height of the people, of the set of people that we are considering. Okay, is this fine? Any questions? Okay, I guess there are no questions, so we'll move on to the next question. So what is the range of intensities along x-axis if a grayscale image is used to build the histogram, requiring 8 bits to store any pixel? Can anyone try to answer this? So you are given a grid.
0 to 7.
Um, okay, you are given 8 bits, by the way. How many different possible values 8 bits can store? Okay, 1 bit, how many values you can different?
256 combinations.
Okay, yeah, that's the right answer. 256 combinations. Okay. So for 1 bit, how many different values can you store? You can either store 0
Two,
or
two.
1, right?
Yeah.
So the bit can only store 0 or 1. Okay. So if we have 2 bits, it's 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. So it is just 2 to the power 2, where this is number of bits. Since we deal here with binary, so the base is 2. Binary, so the base is 2. Okay, so ultimately we have 8 bits here. So 8 bits will lead us to 2 to the power 8 combinations, which is nothing but 256, as mentioned by one of our attendees. Okay, so we know that binary starts from 0, so intensity values intensities will range from 0 to 255. So these in total are 256 values. Okay, is this question clear?
Instead of grayscale image, if they give some other image, how it will vary the combinations we have to take?
Okay, so if we consider RGB image, so how many channels do we have in RGB?
Three channels will be
Three
there.
channels. Okay.
Yeah.
So for each channel, if I say that for each channel, every pixel is encoded with 8 bits. So how many
Okay.
total combinations of colors can you get?
Yeah, will it be like 3 power of
Uh,
8?
no, no.
No. 8 bits, 3 channels are there.
So how many total bits? Okay, I said that for each channel you have 8 bits for every pixel.
Oh, okay. 8 into 8 into 8, 8 cube.
Yeah, 8 cube or 2 to the power, not 8 cube, sorry, it's not 8 cube. So for each channel, every pixel, you can have 2 to the power 8 combinations, right? So you have how many channels? 3
Okay.
channels, right?
Yeah.
How many different combinations you can have? So in total for every pixel you have 24 bits. 8 into 3. Yes.
Okay.
I mean, including all 3
Okay.
channels, you have 24 bits. Uh,
At 24 bits,
so for every bit, you have two possible
we have.
combinations, which
Yes.
leads us to what? Which leads us to 2 to the power 24 combinations. Is it fine?
Total combinations will be 2 to the power of 24.
Yeah,
Okay.
total number of
Okay.
colors that
Thank
you
you.
can, different colors that you can specify. Yeah.
Okay. Yeah.
Okay.
Thank you so much.
Okay. The next question is actually quite famous question in terms for image processing people, and it's kind of a long answer to do it. So we'll go step by step here. So our question is, Otsu thresholding algorithm aims to do what? Minimize the intra-class variance, maximize the inter-class variance, maximize the intra-class variance, or minimize the inter-class variance. Can anyone say the answer based on the lectures? I think it was done in lecture one, if I'm not wrong. Otsu thresholding. Yeah, it's done in lecture one. Yes. So, okay, what is Otsu thresholding used for? What was its
Maybe,
intention?
to
Sorry,
select the threshold value, sir.
threshold values for doing what?
Uh,
Okay, that's fine. But what was the intended application of Otsu thresholding?
Segmentation for image segmentation.
Yeah, it's like binarization of an image. So you want to cluster the image into foreground and background, if you remember that. So in lecture one we are given two methods. The first is the expectation maximization method, and the second one is the Otsu thresholding method. So this question was for Otsu thresholding method. Yes. So someone said it right. It maximizes the interclass variance. Yeah. So if you maximize the interclass variance, the separation will be more. That's what the idea is. But equivalently, you can say that it minimizes the intra-class variance. That means within a class, you want to keep the variance minimum. So yeah, the answers are A to B, but we'll derive how to do it. Okay. So first, for that, I need to define what intra-class and inter-class variances are. Now, I'll define a few quantities here, which will be which will not be similar to that of lecture notations. But if you have any doubts, you can always contact me. So W naught is the probability that a pixel the intensity value belongs to class 0, belongs to class 0, and W1 is the probability that intensity value belongs to class 1. Okay, so once we have these two probabilities defined, Well, we have not defined it. We are just stating what it means. Mu naught and mu one are the means of mean intensities. I'll write it this way. Mean intensities of the two classes. Okay, I guess people are still joining out here. Okay, sigma naught, sigma 1 is the standard deviation of the two classes. So mu t refers to the mean of all intensities. It is independent of any class, and sigma t is the standard deviation of all the intensities. So can anyone tell me, when I just define mu and sigma, what kind of distribution I am implicitly assuming for each of the class?
Normal distribution only.
Yeah, it's not the standard normal, but yeah, it's the Gaussian distribution with given mu and sigma. Yes. So if we have only this first order statistics, which is the mean, and second order statistics, which is the variance or the standard deviation, we assume that we have Gaussian distribution to make our life simple. Okay. So now I'll mathematically write what these things mean. W naught is what? Probability that it belongs to class 0. So before I define it mathematically, I should just draw a simple diagram to understand what is going on. So we have something like this, where this I'm considering it as mu naught, this I'm considering it as mu 1, and there is some small t threshold. And what is this? This is the intensity in this axis, and this is the frequency. Okay, what plot is this based on the classes lectures? Frequency versus intensity. What is it called?
Histogram.
Yeah, it's the histogram of the image. Okay. So it is assumed that the foreground and background are uh, separable. I mean, you can see that there are two separate modes for it. This assumption is required to make use of Otsu's algorithm. Okay. So W naught is given as some k equals to t to capital L minus 1. So L can be similar to that of 256 levels that we discussed earlier. So here it will be T to 255, but I am writing it in general. So since it's a discrete, uh, and the histogram is discrete, so if you want to compute the probability belonging to class 0, so what we'll do, we'll check this length, area under this curve from T to L minus 1. So okay, so L minus 1 will stand somewhere here. Okay. So similarly, I define W1 as summation of k equals to 0 to t minus 1 pk. So these two gives us the probability that any given intensity belongs to class 0 or class 1. Okay. Now next we need to find the mean. We need to define the mean. What is mean? Mean is, mu naught is the mean of the pixel values in class 0. That means class 0 is from t to l minus 1 k into probability that intensity k belongs to class 0. Okay. So we'll expand this further. Probability that k belongs to class 0. Okay, I'll write this as probability it belongs to class 0, probability that this belongs to class 1, just to make it clear. Okay. So given that, so we need to find the probability that the intensity k belongs to class 0 is probability that uh, probability of class 0 given a intensity value k into probability of k upon probability of class 0. This is coming from Bayes' theorem. Okay, so can anyone say what can we say about probability of class 0 given intensity value k for mu naught? It should be 1, right? Because the range here belongs to class 0 itself. See, the range over which we are summing this uh, terms, that range already belongs to class 0. So probability that we have class 0 given an intensity value k for mu naught, specifically for mu naught, is 1, right? Any doubt about this? Okay, so I can write this as probability of k upon probability of c naught in short. So what will be my mu naught ultimately? Summation over k equals to t to l minus 1 k into probability of k upon probability of c naught. So similarly we'll define mu1 as k equals to 0 to t minus 1 k pk upon probability of c1. It will come in a similar fashion. Okay, so what is mu t now? Mu t is the mean intensity value over all the
Hello.
intensities. Yes.
So since the T of C naught given K was 1, because if we take any, like if you want to find the probability of C naught, given that K, since all the point, like all the K points belongs to C naught, so it will be obviously 1, right? Is
Yes,
that
yes,
the logic?
yes, yes, yes.
Okay, and thanks for
Yeah, yeah,
confirmation.
because if you see the summation range, so all the k
Yeah,
values lie in the c naught
C naught
class.
only. Okay, okay.
Okay, so the total probability, the mean of all the intensities is given by k equals to 0 to l minus 1 kpk. So I would like to break this down in such a way that I can include mu naught and mu1, which is simple k equals to 0 to t minus 1 kpk plus summation of k equals to t to l minus 1 kpk. Yeah, it's just the same. We just broke out the summation part into two. uh, Now using this and this, and it can be clearly seen that this part, probability of c naught and probability of c1, is independent of the value k, right? So we can just write it as, we can write this summation of k equals to 0 to t minus 1 will be what? Probability of C1 into W1, and this will be probability of C0 into W0, which is, oh, oh sorry, this is probability of C1 into mu1 plus probability of C0 into mu0. Okay, so this is how we defined earlier. Mu t is mu1 w1, w1 mu1 plus w0 mu0. Okay, so this part is clear, that the total, the mean intensity value over all the intensities is just a weighted sum of the intensity values of each class, where the weights are just the probability values. Okay, so now we need to define the class variances, because our question is about class variances. Okay, so first we'll define sigma naught in a similar fashion. Summation of k equals to t to L minus 1 p of k given c naught k minus mu naught whole square. This is just a simple formula for variance that we are applying here. Yes. Okay. So which we simplified earlier this expression to be probably pk upon w naught into k minus mu naught whole square. Okay, so this is the class variance for class 0, and we'll similarly write it for class 1, 0 to t minus 1 pk upon w1 into k minus mu1 whole square. And what is the total variance? It's just over all the intensity values. Oh, sorry. Okay. Ek into k minus mu t whole square. So this is the total variance. Now we define the two variances that we need to compare. The first one is the between class variance, which was given in the slides as sigma b square as w naught w1 mu1 minus mu naught whole square. Okay, which can again be written as omega naught mu naught minus mu t whole square plus omega 1 mu1 minus mu t whole square. We'll prove this. This equality will prove it. Okay. And then the next thing that we did, we want to check is within class variance, which is the intra-class variance. So the intra-class variance is, or the within class variance is given as w naught sigma naught square plus w1 sigma 1 square. Okay. So first we'll prove the equality, that these two expressions are indeed equal. So let me write this as number 3 and let me write this as number 4. Okay. So sigma b square, I'll use number 4 first. Mu naught minus mu t whole square plus mu1 minus mu t whole square. So what is the expression for mu t that we got? This one. Okay, my labeling might be wrong, so I'll just write it as A here. This is equation 4, and I'll use mu t as w naught mu naught w1 mu1. Okay, plus omega 1 mu1 minus w naught mu naught minus w1 mu1 whole square. So this is coming from equation A. Okay. So what can be done next? We'll just try to simplify this. We'll take mu naught into 1 minus w naught minus w1 mu1 whole square plus the same thing out here, 1 minus w1 minus w naught mu naught whole square. Okay, fine. So once we have this, what can be done? W naught times, this is what? 1 minus w naught is? Minus w naught is what? Can anyone say that? What is w naught and what is w1? Okay, I guess people are lost somehow. W1 is the probability that a particular intensity value belongs to class 1, and W1 is the probability that any
For
intensity
class
value
1.
can belong to class 1, and W0 is for class 0. So both should sum to 1, right? Because they are the only two classes that we are considering. So 1 minus W0 is W1 minus W1 mu1 square plus same thing out here, mu1 W0 minus W0 mu0 square. Okay, so what does this lead to? W0 W1 square into mu1 mu0 minus mu1 whole square plus W1 W0 square mu1 minus mu0 whole square. So if I take this as common, minus mu1 whole square W1 plus W0. So we know that these two sums to 1. This is equals to 1. So we derive that expression that we these two, equation 4 and equation 3 and equation 4 are same. That's what we derived till now. We still have to see how within class variance and between class variance are related. So this is equation 3. Okay. So to finally solve the question, we need to relate the two variances, the within class variance and between class variance, which is sigma w square plus sigma b square. This turns out to be the total variance, sigma t square. So this is the claim I made. So once this claim is made, we can easily choose which all options are correct in those 4 options. Okay. Okay. So I'll just expand this from the definitions that we have. For within class, we have W0 sigma naught square plus W1 sigma 1 squared plus W0 mu naught minus mu t whole square 1 mu1 minus mu t whole square. I just replaced the expressions that we came across, sigma b with equation 4 and sigma w with the within class variance expression. Okay. So what can we do here? W naught times sigma naught square plus mu naught minus mu t whole square. I'm just collecting the terms. Okay. So where are we heading to? Okay. So we'll first look at sigma naught square properly, which will lead us to an interesting expression. A equals to t to L minus 1, k minus mu naught whole square, tk upon w naught. So if we expand this quadratic thing inside, which will give us k naught k square plus mu naught square minus 2k mu naught times pk upon w naught. And I'll just open it up, plus mu naught times summation over k equals to t to L minus 1. Square pk upon w naught. Minus 2 mu naught times summation over k equals to t to L minus 1 pk mu naught square upon w naught. Oh, sorry, there is no mu naught square. Sorry. Yeah. Okay. So this part is fine, right? So I'll check these expressions now. What is this expression? Here k missing. What is this expression given in blue? What is w naught? This thing is equals to w naught, right? Like we defined earlier. So the whole expression will be 1. We are dividing w naught by w naught. And what about this expression? What is this equal to?
Mu naught.
Yeah, exactly. This is mu naught. That's how we define mu naught, right? So ultimately what we get is summation over k equals to t to L minus 1 k square pk upon w naught. So this is what? Mu naught square. This is minus 2 mu naught square. So we get the expression minus mu naught square, which is quite familiar if you remember the statistics. how to compute variance. This is the other formula for computing variance. So we now look at this first expression out there, and we try to simplify this first expression. W naught times sigma naught squared plus mu naught minus mu t whole squared is, we'll just write out that expression, k equals to t to l minus 1 k squared pk upon w naught minus mu naught squared, and if we open this quadratic out here, mu naught squared plus mu t squared minus 2 mu naught mu t. Okay, so this turns out to be what? Okay, I'll just multiply it directly. So it is k square pk, this mu naughts are cancelled, plus mu t squared w naught minus 2 mu naught mu t w naught. Okay, so I'm just doing algebraic manipulations out here. And similarly for the next one, if I see mu1 minus mu t whole squared, it will turn out to be in this similar expression, k equals to 0 to l minus 1 k squared pk plus w1 mu t squared minus 2 mu1 mu t w1. So what are these? So this expression is nothing but the sum of these two, right? Which can be written as, in total, k equals to 0 to l minus 1 k squared pk plus mu t squared times w naught plus w1 minus 2 mu t times mu naught w naught mu naught plus w1 mu 1, these two terms. That's all. So previously we have seen that w naught plus w1 is 1, this is 1, and this we derived it as the mean intensity value, which ultimately gives us this expression, k square pk minus mu t squared. This is again nothing but the total variance. Okay, so now we derived a relation between within class and between class variances to that of total variance. So here we note that sigma w squared, sigma b squared are dependent on the threshold value t, but sigma t squared is independent, because of course this is the total variance of the intensities. It should be independent of the threshold value. We use it for binarization. Okay, so what was our initial question? It was Otsu's thresholding, which is what, if you remember in the class, we want to maximize over t between which varies from 0 to l minus 1, the between class variance, right? So between class variance is a function of t, as clearly been seen, because we have this dependence on t part. All these expressions, the summations, are dependent on t. So between class variance is dependent on t. So we want to maximize the between class variance. That's the way it was defined in the class, and that's the aim as well. So which equivalently can be given as maximize over 0 to t L minus 1. What is sigma b square t? If I use this expression, sigma b squared plus sigma w squared equals to sigma t squared, right? Yeah. So it will turn out to be sigma t squared minus sigma w squared of t. Okay, people are still joining. Fine. So Otsu's thresholding is what? I'll just rewrite it. We want the argument. That is the argument which maximizes the between class variance, or the argument which maximizes this quantity, total variance minus the within class variance. So this leads us to the optimal threshold T star, which we'll use to binarise the image. This is the main aim of Otsu's thresholding. So here, as we can see, that this can again be equivalently written as R max of 0 to L minus 1 minus sigma W square of T. Is it fine? Because this is independent of T. So whether I add something or not, the argument will not change, right? The value of T will not change. Only the value of function, which is this thing, will change. Is this point clear? I guess it's clear. No response from your side.
Yes, sir.
Yes, it's
Okay,
clear.
fine. Okay, so if you want to find a maximum of something negative, we can directly do the minimum of that, right? Why to keep that negative sign? So this gives us sigma squared of t. So ultimately, it's the same thing, which gives us the same threshold value t star. So what this one means is we are minimizing within class variance or intra-class variance. And how it was originally defined is maximizing interclass or between class variance. Okay, any doubts in this question, since it was kind of big? So our main question was just to understand what Otsu thresholding algorithm aims to do. So whether it minimizes intra-class variance, which is true, maximizes the inter-class variance, which is again true as we saw, maximizes intra-class variance, no, minimizes inter-class variance, no. So how we try to prove it? We first define the probabilities and the mean intensities and the standard deviations for the two classes and a total for the whole empirical distribution that we have. So mathematically we can write it in these forms given these histograms, and if we define mu naught, mu1, mu t accordingly, we see that mu t is w1 mu1 plus w naught mu naught, and then we just checked for the class variances sigma naught squared, sigma 1 squared, and we simplified it to this expression, and we defined between class variance, which can be written in these two forms, and within class variance, which is this one. Given these two, we first made an equivalence between this equation 3 and 4, which was just simple algebraic manipulation by using the value of the total mean intensity value, and then we try to relate the within class variance and between class variance. Once we get this relation, yeah, once we get this relation that these two sum up to the total variance sigma t squared, we just check for the basic principle of Oates thresholding, which is maximize interclass variance or between class variance, which is again equivalently written as minimize within class variance or interclass variance. Okay, so is this question clear?
Yes, sir.
Okay, fine. I guess we are 10 minutes past the actual time. So please make sure that you people join early. I guess many people join pretty late. So it's not that convenient for me to switch tabs and then admit you to the meeting. Okay, if you have any questions specific to this session, you can just tag this today's date and week 0 discussion, week 1 discussion in the discussion forum. Else, if you have general questions, you can always post it in the discussion forum. Okay.
This note will be shared, right?
Yes. This will be shared through the website. The NPTEL team will be forwarding it to you.
Okay, not in the discussion forum.
No. Like the one that you get announcements, I guess you will get an announcement for this as well. That these these notes are up there. Yeah.
Okay.
Okay, then thank you for joining. I'll see you next week with the next set of lectures.
Yeah, this thing is completely for 12 weeks, right?
Yeah. This weekly thing is for every. For every lecture, for every week's lecture, we'll do some practice problems on related to that.
Okay, this is really helpful. Thank you.
Oh, okay. Yeah.
Yeah, and like I have one question. Like in this image transform, like in lecture 3 and lecture 4, so was doing image transform, right?
Yes.
So there was a lot of math that there are a lot of formulas also.
Mm-hmm.
So the main thing was like I understood is the image transform is like converting one like the representation of image into another like will be transforming the like the pixel values into different values so that to find a different feature represent like to get more to get more data, right?
Yes.
Okay.
I mean,
So
see,
like
in that different domain, you get to see the different characteristics of the signal, and
okay,
we tend to use those characteristics to process the image. So that's
okay,
why,
like I didn't get any application kind of thing to like if this cosine transform and sine transform and also is it really used in the real life or like I didn't find any application for it.
okay. The DCT, that cosine transform, is mostly used for image compression.
Image compression, okay.
Yeah. I mean, both of them are equivalent. You can use either one of them, but DCT has some nice special properties which helps us using it more than DST.
Okay, so it's like almost all the things are general. So if we only understand the concept, is it's enough not to remember all the things, right?
Yeah, these are the introductory lectures. These are just
Okay,
primers for your main computer vision course. So if you see the
okay,
next lecture onwards from the next week, they are the actual computer vision things. These are just some basics of image processing. That's all.
okay. Even the image transform thing is also basics.
Yeah, these are just image processing. Yeah. So you might
Okay,
want to pre-process image before using it for any computer vision application. That's the reason this has been given in a overview for
okay. So
week
we
one.
can think of it as a black box. Like if we want to transform image, there are some rules like we can apply those formulas and stuff, and then the image would be like transform. Because I didn't have time to go deep into it, so I'm thinking it was as a black box to transform the image into another representation. Is
I
that
mean,
enough?
I think it's enough for this course. I mean, I'll have to see
Okay,
the next content what's up there. I think you might
okay,
need some of it, but the point is, I will not recommend it to use it as a black box.
okay,
Yeah, there are two courses involved in it: digital signal processing and digital image processing. So there you will have detailed explanation of those transforms.
okay.
Um, okay, then I'll stop this session for now.
Yeah.
Thank you
Thank you.
for
Thanks.
joining. Hope to
Thanks
see
a lot,
you
sir.
next week, same time. Yeah.
Yes.
Bye.
Thank you.